Hey guys, my name is Greg Pereira, as was said. I'm a software engineer in the Emerging Technologies Department at Red Hat, and I will be speaking on the llm-d project, which I've been working on for the last 7 months. So this is an agenda. We've got about 40 minutes of content to cover in about 20 minutes, so please bear with me. First, we're going to talk about what llm-d is. We're going to talk about the challenges that it's meant to solve. We're going to walk through the architecture to kind of contextualize those challenges and how they're being solved. We're going to touch on our open source strategy, and then why, as you members of the PyTorch meetup, should care about this. Then we're going to transition to some hands-on examples. We're going to trace a basic inference request through the system, and we can see the scheduler in action. Then we're going to do 2 specialized examples. One, the precise KV cache-aware routing, and understand what the KV cache is. We'll do a technical intro. And then we're going to talk about Prefill-decode disaggregation and how you can optimize your workers for the specific workload that you're targeting. So what is llm-d? llm-d is an open source Kubernetes native distributed inferencing system built for scale. It is a open source collaboration between a few different companies, Red Hat, IBM, Google, Hugging Face, and others. It's meant to be deployable anywhere. We're targeting as many Kubernetes environments as we can and a plethora of specialized hardware backends. And it's supposed to boast a distributed and pluggable architecture. So if you have your own container images you want to bring, your own kernels, you can bring them. So when people pitch me a new system or application, my first question is always like, why do we need this? Why can't we just solve these existing challenges of deploying AI applications on Kubernetes with regard to scalability, reliability, and speed and efficiency? And to understand this, I like to walk through a compare and contrast of traditional web applications and this concept of a modern AI application. The first way in which these 2 applications differ is in terms of the request traffic. So we all know traditional web applications have fairly modular server operations that happen per request. We think of serving the weather here, right? If someone's checking the weather, it's probably as difficult to serve it to person A as it is to person B. And so the overall load of the system is determined by the human element of the traffic. How many people are checking the weather or sending their email, right? For AI applications, this is not the case because there's an additional vector which gets computed into this load of the system, which is that every inference request is not built the same. You can have a 3-second, a 3-minute, or for agentic workloads like a 3-hour inference request, and those look totally different in terms of how expensive they are on the system. And this causes challenges when we consider scheduling. On the left here, you can see an example of a typical modern load balancer doing something like round-robin routing here. But this pattern totally falls down when we look at how LLM requests need to get routed across the system. Put aside the right bucket that's empty for now, but if we had 3 small inference requests that got routed to bucket A and 1 larger inference request that got routed to bucket B, there are certain conditions where it might be more efficient to still route to bucket A if those 3 requests are smaller or if we've previously done some of the work already. We'll touch on that in the KV cache section. The next way in which these application profiles differ is in terms of the hardware backends that they target. Imagine that you're building a CPU-based application. You could build ARM64, AMD64 containers. The truth is you really don't care. As long as your workload gets scheduled, your source code will function the same on both. This is not the case for AI applications, as I'm sure many of you know, that the source code that you write is usually very highly coupled to the backend that you're targeting. This is a totally net new request in terms of deployment. Like, we've never seen this pattern before where the system needs to understand based on the request to map it to a specialized place. This is built into the abstraction of deployment in general. And this should help to visualize this problem a little bit, right? Here we see a request to Llama 3.3, which in the end will need to get routed to this Google TPU backend, whereas a Mixtral, in this case, request will need to get routed to an NVIDIA GPU backend. Gotcha, thank you. So the final category that we're going to compare for the 2 application profiles is in terms of the scalability of the system. Kubernetes was built to scale CPU-based applications. RAM is very granular. You can go as little as much as you want, and CPU is fractional. So this is very native to us. For GPUs, this model falls down on Kubernetes. Traditionally, for scheduling, it's all or nothing. Either pod A gets your GPU or pod B gets your GPU. Even if you can get around these scheduler issues, because there are some hacks you can do, the real challenge and bottleneck has always been for the amount of RAM available on the GPU. I like to use the example, you have a model server with 40 gigabytes of memory, you split this into 2 pods to handle more requests, and all of a sudden you can't load it into memory. Additionally, GPUs are expensive and they're hard to get your hands on, as we saw with Steve's talk at the beginning. So typically what you have is what you have. And so this creates this kind of different dynamic in terms of when you're scaling a system. For CPU, it's can I get more or bigger boxes, in this case pods, but for GPU, it's about distributing requests across your system. Is there no bottlenecks here? And also, can I get the maximum utilization out of my GPU worker here? So let's step through the llm-d architecture and understand a little bit about how we solve these challenges. So the entry point to the system here is the inference gateway. This is an Envoy pod that Huamin was talking about, and for those who are familiar with it, requests will come in through the inference gateway. It will consult with this inference scheduler, which will understand some routing considerations and append headers to the label that initially came through the inference gateway. This inference scheduler is continually watching and reconciling on this inference pod. So we see there are some workers here for prefill and decode, or you could have a generic unit of inference. If you get another one added to the pool, this will automatically be picked up in that reconcile loop. Additionally, for this scheduler, you can have different profiles configured for prefill and decode if you're specializing your workers. So you could route to one of them or the other if you're doing something like PD. And you can also route on specific metrics where you can say, hey, maybe I care more about a KV cache hit than I do a load. And so I'm willing to let my system wait through a queue to utilize some compute that it's already done. Then there's this inference pool abstraction, which get links to the various vLLM workers that we have. This is just done by basic Kubernetes labels and selectors. And then there's this shared prefix caching. This represents the Nixel sidecar. This is a container that sits inside of our vLLM decode pods, not our prefill pods. And this initiates a KV transfer between decode and prefill if you are splitting up the two stages of inference. We'll talk more about this later. And then there's finally this piece about independent prefix caching, where we're extending our inference image with LM cache to be able to understand, have better awareness of, and do operations on the KV cache. Two other pieces I want to call out here really briefly. Body-based routing, we don't currently support this. This is an upstream component of Gateway API inferencing extension. We're looking at this in the long term for the roadmap. And then the variant autoscaler, again, we don't support this right now. We're hoping for v04 release, but this has two really cool use cases. One, you could input SLOs for inference, and it could dynamically configure this topology of the system to maximally meet your SLOs, like if you care about time to first token or time per output token more. The other use case is like Prefill-decode hot swapping. If you have a workload where you're generating a lot more tokens than you are in terms of the workload of doing the prefill or processing these prompts, then you could swap a prefill node over to a decode node on the fly. So this is a closer look at the scheduler. We've got different scheduling profiles, like I said, that helps it understand and how it can target these different types of workers. There's the first phase is the filter, where it selects everything. We saw how this inference pool has different worker types. It'll select the ones specific to the profile that it's working on. If it's doing PD, it'll select just that, or if it's not, it'll select everything. Then there are the scores. You can define metrics on which you want to do your routing, and then you can apply weights to them. This is where I was saying if you care about KV caching more than load, you can define that as a weight. And finally, there's the selection. This is just a math function which will determine of these scores, which one am I going to select to route to. There's additional processing that we do per profile, which is this piece right here. And then we also see the request API. This is this concept of you can batch requests into the inference pool, and then as workers become available, they can pull down and churn through these requests, but we're not overloading our model servers before they're ready to pick up the work. So these are some of our open source collaborations, and this is really our path forward for llm-d. Like, we've talked about a lot of complexity here, and we just do not have the time to build all the different pieces of this stack. So we're partnering with other open source communities. Everyone can carve out their niche in inference, and we can work together as a community to build this. Examples of this are Leader Worker Set, open source project out of Google. This is how we're supporting the wide expert parallel pattern for deployment, rolling out across not just multiple devices, but multiple nodes. The Gateway API inferencing extension, another open source project out of Google. These are solving the two challenges of intelligent scheduling and targeting the specialized backends. LM Cache is our extension to the inferencing image that we touched on earlier that gives the inference image awareness of the KV cache. And then finally, we're actually driving a lot of our server optimizations upstream to llm-d. We talked about the routing sidecar initiating that Nixel KV transfer earlier. This actually got merged upstream, the vLLM side for the support of this, for the v010 release, and we hope to include the dual batch overlap as an optimization to the wide expert parallel pattern in vLLM release 0.10.3. So why should you all care? The first thing is that we're targeting every Kubernetes environment we can in as many specialized hardware backends. Yes, we're looking mostly at scale deployments, but really we want to meet developers where they are and drive research on these patterns, right? So a big part of this is also supporting things like Kind and Minikube for local development. So you should be able to run this. The next piece is that these are guides, right? These are abstractions. You don't need to understand all the complexity of this distributed inferencing system to deploy this in 3 buttons and get good enough performance. You can start to peel the onion as you get more comfortable and optimize whatever you want to, but you don't need to worry about every piece of this project. And finally, it's just performance for costs. Like you could go to a specialized hardware vendor or a frontier model provider and work with them to build a stack or have them build it for you. Cost you an arm and a leg, and you'd be locked into their platform, but you could do it. Or you could come to llm-d, use something that is totally free and get pretty much equivalent performance and bring whatever optimizations for your use case that you want. So we're gonna jump into the demos now. First, we're gonna do some level setting on tracing a basic inference request. Then we're gonna talk about the KV cache, and then we're gonna jump into Prefill-decode disaggregation. So I've got a demo here for the inference scheduler.
Okay, now that we've deployed, let's trace a request through the logs. So we're gonna send off a curl request. We're gonna zoom up here. Okay, so first we can see that the scheduler is receiving pieces of the request until it hits the EOS token, and it understands that a full request has been assembled here. It's going to then understand that there has been a bypass to the saturation check. This is a concept from the upstream gateway API inference extension, where you can set inference models to have a criticality, i.e. a request that goes to this model within the inference pool is a critical workload, and I don't want it dropped. Otherwise, you can enable requests being held at an inference pool until workers have enough capacity to pick up that request. But I've bypassed that here. Next, we're going to need to pick the profiles that are going to run for the request. And the plugin you can see here is the single profile handler. So we understand there's only one profile of work that we're going to do here. Then it's going to understand for that single profile handler, the profile we're going to run is the default profile. And it will begin to manage the scheduling work that's going to happen for this default profile. So in the default or in a profile, there are 3 steps. There's the filter, the scoring, and the selection. So let's jump into the filtering, where it's going to filter of all of the pods available to us in our inference pool. We're going to sort through them by some label to identify which ones are we going to target. Again, because we're doing this single profile, this functionally isn't going to do everything. We're going to return every pod within our inference pool. But we're going to filter by label, as I said earlier. The label we're actually filtering on, which it doesn't show, is this llm-d.ai/inference serving true label. This is just showing for the pods that it has filtered what all the labels available to are, as well as some metrics on it, such as KV cache utilization rate, as well as like requests that are queued and requests that are run. This is a summarization step saying that our filtering has been completed, and we'll be able to see the results of this in the before step of the scoring plugins, which take place next. So we've got 2 different pods here that you can see that have been filtered out through our filtering step. Then it's going to run the scorers. We've got the load-aware scorer is the only score we're using here. It's going to summarize to us that this work has been completed, and then we'll be able to see the results of this in the before piece of the picker plugin. So we can see there are actually 2 pods here that we got filtered out for, and this is the first pod, and it's got a score of 0.5, and this is the second pod here, and it also has a score of 0.5. And this is because the running queue size for both of these workers is 0, so in which case it treats them from a load concept as totally equal. But then it still needs to select one from the 2. In this case, it's going to default to using a random picker between the 2 if the scores are exactly the same. And then after running the picker, you can see that it has selected out 1 pod for us to use with a score of 0.5. So now it's going to understand every piece of work we talked about. There are those 3 steps within the scheduler. All of that is done for this specific scheduling profile. So that was after the scheduler profile has succeeded. Then it's going to need to pick the profiles as well as process the results of the profiles. So there are multiple profiles that you could have. In this case, we have a single one. And this is for things like Prefill-decode disaggregation. The system still needs to understand which do I need to hit first of the 2 profiles that I have available to me. and then it will lock in the pods that it's going to use for that, essentially. And then from the scheduler perspective, the request has been handled, and everything below here is where it interacts with vLLM, as well as receives data from vLLM to set headers back onto the request that's going to be forwarded out to the gateway. And then finally, we have where the response gets streamed back to it. It considers the response as generated and fully completed, and it will send it back to the gateway.
Okay, so the KV cache. I might skip through some of these pieces because Luke already touched on this, but specifically we're going to focus on its transformative effects in terms of how scalable it is for transformer models. And because of that, we're going to focus on attention because this is the least scalable part of the transformer model architecture. And we're going to step through decode phase in terms of generating a token. So for those who don't know what attention is, we'll start with some context setting here. They went to chase the steer who got loose. We as humans will look at this sentence and we will see the words chase and the and understand, steer is probably an animal here in this case, rather than the verb to steer right or left. And this is what attention is, to basically weight your most previous tokens against the previous context to kind of influence the values and probabilities that come next. I have technical definitions here for query key and value, but I'll give you a human definition instead because we need to move fast. I like to use the party analogy. So I don't usually go to parties, but when I do, I know no one there. And because of that, I usually have an interest through which I relate to people. In this case, let's say music. That is my query. I'm going to match my query against the little name tags that everyone wears, which has their name, but their interests. Based on how that query and how that key match up, there exists a probability that I probably care about what they're going to say more than some random person. And this is the basis of attention. We have a formula here for deriving this, which we're going to kind of step through in the values of calculating a token. But we basically take the softmax of matching up that query and key token, as I said. We're dividing by the dimension of k, which is the key matrix. This is in terms of scaling across the full context as it grows. And then we're going to apply it to the values. So when you calculate a token, what you're going to do is you're going to take your query token, which is your most it derived from the embeddings of your most recent token you generated. You're multiplying this by your key matrix, which is all your previous keys that you've calculated. You're applying the softmax. This is the there exists a probability piece to normalize the probabilities. And then we're going to multiply by our value matrix. And this is going to give us our attention weights. We should note here there is more work that happens in the transformer. We're focusing on attention. We're using this as an abstraction for generating a token here, though, because the rest of these operations are linear. So stepping back to this, what is KV caching? KV caching is this concept that we've already calculated keys 1 and 2 when computing token 3, and we're just going to pull those values from cache. So there's a linear amount of work that needs to happen. It's O of 2n because there's two things we actually need to do. We need to first calculate our embeddings in our key and value for the most recent token, and then we need to just feed through this model to calculate our final token, but in this case, it's a linear amount of work. Without this, it's quadratic because you need to calculate token 3, you need to calculate tokens 1 and 2. And then to calculate token 4, you need to start over again because you didn't share those keys and values. Okay, so at this point, when I talk about KV caching, everyone's like, this is such a big deal. Why are you even talking about it? Why isn't this already in our mental model of how we see the world? And it is. The difference is it's at the server runtime level. What we're talking about with llm-d is taking all the great work that Luca and his team at vLLM have taken and distributing it across a Kubernetes system. Now, if you've been doing this multi-turn chat with a LLM and you've had 6 back and forths here, and this gets routed to worker 1 in this case, now all of a sudden it gets routed to worker 2, there are two things that are going to happen. One, it needs to compute all of that work over again, and then 2, it needs to fill up and use this KV cache space on a different GPU worker. And this is bad for those 2 reasons. So we need a router that understands the state of the KV cache and won't make that mistake. It'll route to this pod in this case. So let's step through the demo and understand how that looks.
The precise KV cache-aware example is going to be laid out pretty much the same as our basic inference scheduler request that we looked at previously. The key difference here is that we're going to be grepping for got pod scores in the top left of our inference scheduler logs. This will help us to focus only on KV cache hit versus no KV cache hit rather than the different steps in the inference scheduler logs. Now let's look at the requests that are going to make up this experiment. We have 6 requests in total in 2 different buckets. The first is a cloud provider prefix and the second is the hardware provider prefix. Each of these prefixes are 2 sentences that are shared for everything in that bucket. Every request as well has a one-sentence unique postfix. This will help us to ensure KV cache hits, but still have a totally unique request. Let's take the first request in the cloud provider prefix bucket and dispatch that. We can see here that the scores are null, i.e. we got no KV cache hit on the fresh system, and it gets randomly routed to worker 1. Let's take the second cloud provider prefix and dispatch this curl request. Now for scores, we can see a pod IP as well as a score, meaning it gets a cache hit and it gets routed to that same worker. Let's test out the new hardware provider prefix. We dispatch the request. We see that we get no prefix cache hit, and it gets randomly routed here to worker 2. Let's go back and finish the last of the cloud provider prefixes here. As expected, we get a cache hit, and it gets routed to worker 1 with the other cloud provider prefixes. Let's test the second hardware provider prefix. Again, we see a cache hit, and it gets routed properly to worker 2. And finally, let's test the last hardware provider prefix, which we see a cache hit, and it will properly get routed to worker 2 as well.
Okay, so Prefill-decode disaggregation. We talked about generating an individual token. That is the decode phase. Prefill, as Luca was saying, is the concept that we have a fresh prompt that cannot be pulled from KV cache because it's the most recent prompt. We need to compute all the keys and values of this before we're able to start doing our decode work over and over and over again. So what is prefill disaggregation? It's taking these two different steps that happen in inference and breaking them apart. And why do we want to do that? Because this will allow us to specialize our workers to the workload that they're going to support. Prefill, generally, because you have long context and it's very compute bound, is hard to process. So we don't parallelize this as much. We give it bigger, beefier workers. Decode is lots of repetitive churning on memory bound operations. This we can parallelize. So this is an example of how we might specialize that labor. But it's important to note other worker profile or workload profiles exist. I like to give the example of little Timmy coming home from second grade. His teacher told him to write a paper on World War II, and so he spits in a one-sentence prompt about, hey, give me an MLA-cited paper, and out will come 3 pages of output tokens. Now, if we look at this profile, we've got a ton of decode work. Lots of tokens are getting generated for a small prompt that needs to be processed. And so in this case, we would probably parallelize the prefill operation because we could do a lot of them with these smaller prompts, and we would churn through these bigger amount of batch token generations, or sorry, these bigger token generations at the end. They're not batched. Okay. And then this is just to underscore that this KV cache is the bridge here in this case between prefill and decode. Prefill can compute all of these key values. It'll then transfer it over to decode, and decode can go and use those to do this inference and grab our tokens. Okay, and this is what it looks like in terms of the system. So a request comes into Envoy. It will consult with the scheduler. It'll get the headers appended, same as before. The scheduler is what will tell it, hey, are we doing PD here? And there are some unique cases where even with Prefill-decode disaggregation, you might not use PD. We'll talk about that in a second. But then we're going to route requests to the routing sidecar in the decode pod. Routing sidecar will understand, am I doing PD? If I am, it's going to go to prefill first, then it's going to come back to the routing sidecar, then it's going to go to decode, and decode is going to route back to Envoy. And then on the right here, we're just kind of showing the networking that happens here. The API layer is Nixel. Underneath that, we have UCX, and then we have the different transports that support that. Okay, so why wouldn't you want to do PD when you have PD deployed? Well, imagine a case where you have a prompt that has like 10 tokens. It's very small. It's probably more work to initiate this transfer between prefill and decode than it is to just actually do the work on one GPU. So that's an example. We've also talked about how decode can do both prefill and decode in llm-d, and prefill just does prefill. If all your prefill pods are backed up, then you can route right to decode and it can do both operations. And then with the KV cache hits, we talked about how you might want to reuse some of your work. You can do that as well here. So I've got another 1-minute demo. I know we're at time. Is it all right? Okay. All right.
Now we're going to look at the Prefill-decode disaggregation example. In this example, we're going to understand how when even splitting the 2 phases of inference, prefill and decode, they're still able to work together to resolve inference requests. we're going to start by tracing an individual request through the logs of the routing sidecar to understand how it orchestrates the communication between decode and prefill workers. After this, we're going to send about 30 requests at once and trace the access logs of vLLM to understand which prefill worker is picking up the prefill work, how it's able to transfer those KVs to the decode worker, and then the system is able to resolve inference requests in its totality. We're going to start with an individual inference request here. And now we're going to look at the logs of the routing sidecar. We've got the maximum verbosity on, so we'll see things like the SSRF protection being enabled, as well as that the protocol that the sidecar is running on is the NIXL v2 protocol. After this, we'll see the routing information, however, that first a request is sent to prefill, then a response is received from prefill, and then a request is sent off to decode. And we can see here in the prefill worker, we have a post to v1 completions with a 200 status code, as well as a post for v1 completions in decode after, with some KV transfer metrics that happened in between. Now let's go ahead and send off a bunch of requests at once. We can minimize this because we don't care about the routing sidecar logs anymore. And in this way, we can see that prefill work gets distributed amongst these different prefill workers, and that decode is able to then pick up all of these and solve all of the requests there. It's important to note that requests are not being evenly distributed amongst prefill because the load-aware score is not in use. Instead, there's a queue score, and because we're hitting it with such low numbers of requests,
The queue is almost always empty, resulting in functionality similar to random routing.
All right, and that is it from me. Thank you guys so much. Please check out the llm-d project. Yeah. Go ahead.
Hey, great talk. Looks very promising. I'm curious, have y'all done any benchmarks to compare to kind of traditional session-based routing?
The answer is yes. The performance team would be the people who primarily tackle that. I don't have those numbers, and I can't speak on them, but I'm sure that they have. Go ahead, sorry.
Can I follow up with that? When we show routing, is the routing done effectively by prefix of text of the query?
Yes, yeah. I think right now it'll start with the beginning of the query, and it'll start from there in terms of how many tokens does it get a hit out of the start window that you look at for the tokens. So you can say the window I'm going to look at for a cache hit, you can change that number of tokens. So in this case, you could say I'm going to look at a window of 64 tokens, and then you could look for a cache hit percentage on that for like 90% or whatever it is. But there's granularity to specify how you consider a cache hit versus not cache hit, but it does always start from the beginning of the prompt. It does not enable you to start from the middle of the prompt in terms of that cache hit, if that helps.
Is there kind of like semantic matching of that? Like you could say hello world, you could say hi world.
Yeah, I don't think it supports any semantic pieces yet. I think it's direct token matchup. I think that's it. Thank you.
Thank you, Greg. Okay, so that's the end of our presentations. Just want to thank the speakers for coming out, and thank you for everyone to come out. We'll have more of these events later this year.